In this part of the lecture, we're going to be looking at molecules and bonds. Before we get started into the main part of this section, let's first talk about a little bit of review about what we talked last time. I'm going to give you an example from the periodic table, and I want you to tell me how many protons, neutrons, and electrons it has. So for example, this is oxygen. Here's atomic number. Here's atomic mass. Press pause, figure out how many protons, neutrons, and electrons this oxygen atom has. Okay, welcome back. So protons, remember the protons is equal to the atomic number. Number of protons is 8. Neutrons is the atomic mass minus the atomic number, also has 8 neutrons. And electrons, because there's no charge here, that means it has 8 electrons. What if we had oxygen with a -2 charge? What would that mean? Give you a little bit to think about it. Our protons are still going to be the same because it's oxygen. Our neutrons haven't changed because it's not an isotope. But the electrons, when we have a charge, we know the electrons have changed. It's a -2 charge. Remember, the electrons are negative. And so if there's 8 positive protons, in order to give us a -2 charge, that means we have to have 10 electrons. There we go. So there's a little bit of review, and you can practice a little more to make sure that you remember the different rules that we went over last time. Today, though, we want to talk about molecules, compounds, and then about bonding properties. A molecule is whenever we take 2 like atoms and combine them together. A compound is when we take different atoms and combine them together. So examples of molecules you may have heard about, you often see oxygen written as this, O2. That's a molecule. It's 2 oxygen atoms connected together. Something called C4, methane. That's a molecule. A compound is when you take different atoms. For example, H2O. So we have both hydrogen and oxygen. That's a compound, water. C6H12, O6, glucose. We have carbon, hydrogen, and oxygen in a certain ratio coming together to form a compound. In this picture here, we have sodium. We have chlorine coming together to form sodium chloride, table salt. Something to notice about compounds. Whenever we take 2 atoms and we combine them together to form a compound, we're going to change the properties of that substance. So sodium is actually a metal, chlorine is a poisonous gas. Add them together into a compound and we get table salt, something that we're all familiar with. So whenever we're adding atoms together, we're going to have a new set of characteristics. The way that we combine atoms together is determined by their electrons. So we're going to take a little bit of time and figure out how electrons work. Electrons are situated, so in these previous pictures we looked at, you noticed that the electrons were drawn around the protons and neutrons found in the nucleus in some sort of orbital. Scientists have never seen an electron, so they're not really sure how it works necessarily, but they do know that it is found around the nucleus. It's sometimes drawn in this way, and they call this the orbital model because it's orbiting the nucleus like a little planet. But there's also this is called the planetary model because it's orbiting like a little planet. There's also something called the orbital model where the electrons are just kind of drawn as a cloud. You can't necessarily see the the individual electrons. They're just in this area around the nucleus. We're going to be using the planetary model for now because it's easier to see where those electrons are situated and how they're going to interact with the other electrons of other atoms. So electrons occupy energy levels, and they call these electron shells. Depending on how many electrons an atom has determines how many shells it has and also where those electrons are situated around the atom. So each shell can only have a certain number of electrons, and then it's considered full, and the other electrons have to go then to another shell, then the next shell. Shells that are closest to the nucleus are going to fill up first, and then they're going to move out. So this is kind of like when you're coming into a room. When you're coming into a classroom, let's assume that the students are piling into a room to listen to the professor talk. If the students represent electrons, they would go to the very front row, and they'd fill up that front row first before starting to fill up the next row. And that almost never happens in a classroom. Usually people like to fill up the back and then move forward. But if it was like this electron orbital rule, all the students would fill up the first row. Once that's full, then you'd move back. But only a certain number of students could fit in that first row. The way this works, we're going to use an example here. I'm going to explain how oxygen works, and then we'll look at a couple others and let you practice some. So going back to oxygen, atomic number 8, mass number of 16. We know that the protons and neutrons are in the nucleus. We have 8 protons, 8 neutrons in that nucleus. The electrons are going to be in the orbitals around. In the first electron shell, you can have 2 electrons and no more. So I'm going to put 2 electrons here. Once you have 2 electrons in that shell is full. Any other electrons have to go in the next orbital. If we look at oxygen, we remember that there are 8 electrons because there's no charge, the protons and electrons are equal to each other. So if we've already used 2 electrons, that means that in the next shell, we're going to have the 6 electrons that are left over. And that's all the electrons that oxygen has. However, the second shell can have up to 8 electrons. That's when it becomes full. So shell number 1 can have 2 electrons. Shell 2 can have up to 8 electrons. Shell 3 can have up to 18 electrons. However, 8 is the magic number in all the shells except that first shell. When an atom has 8 electrons in its outer shell, it's stable, or it's happy, if you think about it in that way. But having 8 electrons in the outer shell is good. The outer shell also has a special name. We call this the valence shell. Okay, the valence shell is always the outer shell, and that's important because it's the valence shell that is going to determine how this atom interacts with other atoms. In the case of oxygen here, because it has 6 electrons in its valence shell, it would like to have 2 more electrons, and that's going to determine how it interacts with other molecules. Let me give you another example now, and I want you to draw what this atom is going to look like and where the electrons would be situated around this atom. So chlorine has an atomic number of 17 and a mass number of 35. Pause the recording, figure out how the electrons are going to be situated around this atom. Okay, so we know we have our nucleus here, and we know in that nucleus there's going to be 17 protons and 18 neutrons, but we're going to focus on the electrons. In this case, the number of electrons is going to be 17. Let's draw our first electron shell. We know that it can have 2 electrons. It's full. Draw our next shell. Once it has 8 electrons, it's also full. So far we've drawn up 10 electrons. Take 10 from 17, it means we still have 7 electrons, which means that we need a third shell. And in this shell we're going to put the last 7 electrons. So our valence shell has 7 electrons. Chlorine would like to have one more electron in order to be happier, to be stable. That's going to determine how it interacts with other molecules.